Last time we mentioned that geometric multiplicity is never bigger than algebraic multiplicity. Today we actually prove it. Reckless honesty. I know. Then we define diagonalizable, prove the basis of eigenvectors criterion, and show that enough distinct eigenvalues force diagonalization. Geometric multiplicity counts independent eigenvector directions. Algebraic multiplicity counts how many times lambda appears as a root of the characteristic polynomial. These sound like different species. The proof is the bridge. Because apparently definitions refuse to socialize without supervision. Let K be the dimension of the eigenspace. Choose a basis V1 through Vk of that eigenspace. Since those vectors are eigenvectors, A sends each Vj to lambda times Vj. Then extend the list to a full basis of V. In this basis, the first K basis vectors are eigenvectors. So the first K columns are just lambda times those basis vectors. That forces a block upper triangular form. The upper right block can be whatever nonsense it wants. The lower left block is 0. And that is the part we need. Now apply determinant to Ti minus A. A block upper triangular matrix has determinant equal to the product of the determinants of its diagonal blocks. The factor T minus lambda appears at least K times. But K was the dimension of the eigenspace. So algebraic multiplicity is at least geometric multiplicity. We define diagonalizable directly. A is diagonalizable if there is a basis where its matrix is diagonal. The condition involving algebraic and geometric multiplicity is not the definition. It is a useful theorem that comes after this definition. Suppose the basis vectors are eigenvectors. Then AVJ is lambda j times Vj. That means column J has only one non-zero entry on the diagonal, so the matrix in this basis is diagonal. Miraculously, the columns behave themselves. Conversely, if the matrix of A is diagonal in some basis, then each column tells us AVJ equals lambda j Vj. So diagonalizable is exactly the same as having a basis of eigenvectors. Not a metaphor, not vibes, a basis. Now assume the characteristic polynomial splits into linear factors. For example, this always happens over the complex numbers. Since geometric multiplicity is at most algebraic multiplicity, equality for every eigenvalue means the eigenspaces have exactly enough total dimension to form an eigenbasis. By the eigenbasis criterion, that is exactly diagonalizability. So this is a theorem, not a definition smuggled through customs. Now suppose the space has dimension n, and A has n distinct eigenvalues. Choose one non-zero eigenvector for each eigenvalue. Different eigenvalues give linearly independent eigenvectors, which we proved earlier. Now we have n linearly independent vectors in an n-dimensional space. So they form a basis. Therefore A is diagonalizable. Distinct eigenvalues are not subtle. They just brute force enough directions. Do not confuse sufficient with necessary. This diagonal matrix has repeated eigenvalue 4, but it is obviously diagonalizable. Repeated eigenvalues are not automatically bad. The real question is whether the eigenspaces have enough dimension. As usual, the details are where the tiny monsters live. We proved the multiplicity inequality. Defined diagonalizable as existence of a diagonal matrix in some basis. Proved the eigenbasis criterion. And then proved the multiplicity criterion. Next, we look at what happens when eigenvalues exist but eigenvectors are not plentiful enough. The matrix will have one job. And naturally it will disappoint us.